Gibson here. Today we're going to talk about refraction and how it applies to lenses as we continue this unit on light and its behaviors. So we just finished understanding that refraction, right, occurs whenever we have light that travels across a boundary between two materials that have different speeds. And if that light comes in at an angle, it will bend or change its direction. So how does that apply to lenses, and what are lenses actually used for? We actually relate to these every day, right? We have lenses in our eyes. We put lenses in front of them with glasses or contacts. So very everyday application of this physics principle of refraction. So here's our learning objectives. First, how do we describe real and virtual images that are formed by two types of lenses here? So I'm going to highlight a few things here. The first concept is, what's the difference between a real and a virtual image when we are using lenses? And then we're going to look at two types of lenses, converging and diverging. And most of the work we'll do today actually is with converging lenses. The second objective is, how do we analyze the image that will form when the light shines through a lens? And we're going to have two ways. The first way is what we call a graphic solution, where we use light rays. And the second way is we have a set of equations called the lens equations. So we can do it graphically, and we can also solve lens problems using a little math here. Okay, so that's what we're going to talk about today. All right. So we've already looked at what happens when a light beam, right, hits a prism. We saw this in the lab that we did. So let's put our light ray in here. We'll put in our normal line, and we're going to be going from fast to slow, right? So as it travels through that boundary between air and, let's say, glass, right, it's going to move closer to the normal line. And then we go from slow to fast, so it's going to move further away from the normal line. Okay, so this is the path that the light would take traveling through a prism, a triangular prism. So we could do this for a couple of different light rays through there. Okay, so now what happens if we take a series of prisms and stack them up? Okay, so in the center we have what we call a rectangular prism, and then above that and below that, you could call it, I guess, a trapezoidal prism, and then a triangular prism on the very top and bottom. So we already saw, right, that as the light comes into a triangular prism, it's going to get bent down below the horizontal path that it first started. Same thing for a trapezoid. Now the middle one, when it travels through, there's no angle, right? So it's going to go straight through without any change in direction. And the bottom components will move just the opposite of the top. So what will that look like, right? Here's our one that goes straight through the middle. These will bend towards the center, and the triangular prism is going to bend even more to the center. So notice what this lens does. It focuses the light at a particular point on the other side of the lens. And we call that, big surprise, the focal point. So we would call this a converging lens. Converging is just another name for coming together. So think about the light coming together at a single focal point. Okay. The way we can recognize the lens is that the shape of it will always have the thickest portion in the middle, and that will cause the light rays to converge or come together at a focal point. So the normal name we'll use for it is converging. Sometimes you'll also see the word convex lens. Okay, so that's our first type of lens, and this is the one we'll be working mostly with today. What if we stacked up our prisms kind of the opposite, so that it was thinner in the middle and thicker at the top and bottom? Well, let's do the same thing. We're going to shine our laser through here and see what direction. Now, because we flip these in the opposite direction, rather than converging to a central point or focal point, these are going to spread further apart. Right? So the center one, again, continues to the center, but the next two will spread further apart, and the top and bottom even further. Now, this type of lens, right, clearly the light is not going to converge to a focal point. We call this a diverging lens. And this causes the light to spread further apart. Now, we can talk about the focal point of a diverging lens if we trace the path that these 5 light rays refracted back behind the lens. They will still come together at a focal point, but you can almost kind of think of that as a virtual focal point, okay? If you went out in the sun with a diverging lens, you would not be able to get the light to focus and say burn up a leaf. I'm sure we've all done that before with a magnifying glass. The converging lens that we saw would certainly do that, right? So let's define that. A diverging lens is a lens that's thinnest in the middle, and it causes the light to diverge or spread apart. Another name we have for that is called the concave lens. So diverging or concave lens, we're talking about the same shape, thinner in the middle, thicker at the outside edges. Okay, so those are the two types of lenses, diverging and converging. So let's talk about the anatomy of a converging lens. Okay, so the line that goes right through the center of the lens we call the principal axis. The vertical line that kind of goes through the lens, called simply that, the vertical axis. And then we have our focal point, right? We can have a focal point the same distance on either side of the lens. Another point that is interesting for us to analyze is a distance that is twice the focal point, right? So 2 times the focal length from the lens. Okay, and you'll see in a minute why that point is of interest to us. So the distance between the lens and the focal point we call the focal length. Oops. So those are the key kind of parts or anatomy of a converging lens: principal and vertical axis, the focal points, the focal length, and then 2 times the focal length. This 2F point out here is also of interest to us. All right, now, as we start to look at our analysis methods, we are going to make an assumption here. Now, in theory, right, the lens is gonna, or the light ray is gonna refract once when it enters the lens and then refract again when it exits the lens, okay? And that's, if we follow that, it's gonna make the analysis fairly complex here. So what we're going to do is adopt what we call a thin lens model. So this assumes that we have a relatively thin lens and that we can model the refraction to occur only once. Okay, so instead of occurring twice when it first enters and exits the lens, we'll kind of say what's the net amount of refraction or bending of the light as it travels through the entire lens. So we're going to model it this way. We're going to show the light coming in, hits the principal plane, and then refracts, in this case, down through the focal point. Okay, and this will make our analysis a little simpler as we go forward. Okay, so what are the rules for refraction of a converging lens? So how do we do this graphically? This is the graphical method that we talked about. So we can identify where the focal point and the image will form by using light rays. And the first step is to draw a ray parallel to the principal axis that refracts through the lens and then travels through the focal point on the opposite side. So let's do that. Here's our light ray that travels parallel, and then we draw it down through the focal point, okay? We can also draw one from the focal point and have it refract through the lens and then travel parallel. So kind of the opposite of this path. So what would that look like, okay? Here it comes through the focal point, hits the lens, and then it's going to travel parallel to it, okay? And then the third line we can draw is a ray that will pass through the center of lens and continue in the same direction that it had when it entered. So it doesn't matter what our angle is, because it's going to have kind of offsetting refraction angles, because it's going right through the center of a symmetrical lens. It's going to continue on through the same path on the other side. Right? And again, no matter what the angle is, if it travels right through the center of the lens, it will not change direction or refract. Okay, so we can use these three lines to determine where the image will form. And the reality is we only really need two of these three to be able to locate the image. Okay, so let's move on to that next concept here. So what do we mean by an image? Well, the image is formed by the light of the object, so reflected light coming off of our bird here, shining through the lens, and then what forms on the other side. We call that the image. So if you looked through the lens at the bird, you're technically seeing the image of the bird, not the real thing, not the real object. Okay, similar to when we studied reflection. Remember, the image formed on the opposite side of the mirror, the same distance. Okay, so it's kind of the same concept of an image versus the object. Now we have characteristics of the image: its orientation, its size, its location, and its type. So let's step through that here. So for orientation, it can either be upright or inverted. So when we look at the image, it will look like the bird upright or the bird upside down. So here would be an example of an upright image. Here would be an example of an inverted image. The second characteristic will be the size. Does the image appear to be the same size, or is it larger, magnified, or smaller, reduced? So here would be an example of magnified. Here would be an example of reduced, okay, smaller than the original object. The third is the location, and we're going to describe the location relative to the focal point. Okay? So is it less than the focal point where the image would form between the lens and the focal point? Is it greater than the focal point? Or it could be right on the focal point, equal to the focal point. And then the last is whether it's real or virtual. So here's the rules. If the image forms on the same side as the object, we would describe that as virtual. If the image forms on the opposite side of the object, then we will have a real image. Okay, so those are the characteristics of the image that forms when the light reflecting off of the object, or the bird in this case, shines through a converging lens. All right, so let's see how this graphical method works, okay? Let's say we're gonna look at a few cases here. The first is where the the object is greater than 2 times the focal length away from the lens, okay? So we're just gonna put this black arrow in here and say that's our object, okay? We're not gonna do a fancy bird or anything like that, but it's basically our object. So how will the light shining off of that black arrow create an image through the lens? So remember those 3 different lines we could draw. The first line we're going to put in is the one that goes parallel, so going from the top of the arrow through the lens and then through the focal point, okay? And what we're going to find where these lines intersect is where would the location of the arrowhead be for the image. You'll see here as we develop this. All right, let's use our second rule. This is one that goes through from the image or the object through the focal point and then parallel to the principal axis. So once these 2 lines intersect, that tells us where the image is going to form. Okay, so we, in this case, we get an image on the opposite side. It's going to be inverted, upside down. Notice it's upside down from what the original object was, and it's smaller. Okay, so let's list those characteristics, right? Remember, the first was is the image inverted or upright? Okay, So we see that it's inverted. The size of it is reduced. Okay, so it's smaller than what the original object was. The location of it will be somewhere between the focal length and twice the focal length. Okay, we call that distance d sub I for image. And originally the object distance we label as d sub O for object. And then the type of image, remember, if it forms on the opposite side of the object, then that is a real image. Now, if we were able to have a lab in class, we'd actually put some candles here and look at the candle light, the flame, through the lens, and we would be able to see it by putting a little paper screen, so just like a projector screen, but a paper screen where the image of that candle flame would form on the paper, right at the image location. So that's what we mean by real. We can actually focus that image and see it on a screen, a paper screen. Okay, so we have a real image here. All right, so that's our first case where the object is greater than 2 times the focal length. Let's look at another case where the object is right at 2 times the focal length, and we'll use the same method we did before, right? So we're going to do a line that's parallel and then goes through the focal point. We're going to do a line that goes through the focal point and then parallel, and then here is our image where those two intersect. So let's again describe the characteristics where the image formed. In this case, it's still inverted upside down from the original object. The size of it is the same. You just look visually, you can see that the length of that arrow is the same as the object's arrow length. The location is equal to twice the focal length, and it's on the opposite side of the image, so it is real. Okay, so that's our second case here, where the object is 2 times the focal length away from the lens. All right, let's look at case 3. This is where the object is between the focal length and twice the focal length. So again, we'll use our graphical method here. We're going to have the light rays first go parallel, then through the focal length or focal point, then through the focal point, and then parallel to the principal axis. So here's our image forming over here. So how would we describe it? Still inverted, upside down. In this case, it's larger than the object, so we would say it's enlarged. The distance is greater than twice the focal length away from the lens. That's the DI. And again, it's on the opposite side of the object, so this will give us a real image. Okay, so we're stepping through these cases. All these cases depend on where the object is actually located. Let's go to case 4 here. So in this case, the object is right on the focal length. So again, let's draw in our light rays. First one parallel, then through the focal point. The next one, we can't really draw it through the focal point because the object is sitting at the focal point. But this is where we can use the third method, which has a line that goes right through the center of the lens. So we go from the top of the object through the center of the lens. And notice, in this case, we have 2 light rays that are parallel. They do not converge. They do not come together at any point. So what does this tell us? Well, it means that if we put the object right at the focal length, no image will form. It's kind of like a blind spot for the lens, okay? It cannot form a nice, crisp image if the focal length of the object is right at the focal length. So if there's no image, we have nothing to say about the other characteristics of it, right? We can't say whether it's inverted or upright. We can't say if it's larger or smaller. All we can say is that for case 4, we will have no image. All right, case 5, we now move the object to in between the focal point and the lens. So we can put our first line in here. That's easy. The second one, we have to start at the focal length, go through the object, and then to the lens in parallel. So we can use that, but again, notice these 2 lines on the opposite side here are not going to converge. Now, do we say that there's no image? Well, hold on. Here's what we can do. We can take these 2 lines and extend them back onto the object side. And where they come together is going to form an image. But if you remember, if the image forms on the same side of the object, this gives us a virtual image. Okay, so it's non-inverted. It's the same direction pointing upwards as the object. The size is larger. The location of it is less than the object location. Okay, and also it's going to be, I'm sorry, greater than. It's going to be further away from the lens than what the object was. But it's going to be on the same side, so we treat that as negative. And then the last is, since it formed on the same side as the object, it's virtual. Now, the only way we can observe a virtual image is by actually getting our eyeball down and looking through the lens and seeing what appears to be the object, but it's really going to be the image, and it's going to be much larger. So this is kind of how a magnifying glass looks like, right? You look through the magnifying glass and you see an enlarged version of the object, and that works as long as the object is closer to the lens than the focal point. Okay, so those are our 5 cases. The first 3 give us real images, all inverted. This 4th case gives us a no image, and the 5th case gives us a virtual image. So here's the rule for virtual images, right? They are always on the same side, and the image distance, di, we treat as a negative value. Now, let's get into the math here. There are ways to solve for these locations using a formula. So here's the lens equation. 1 over f equals 1 over di plus 1 over do. Now, di and do are the distances that the image and the object are from the lens, right? It's these up here, these values or distances here. F is the focal length. How far is the focal point from the center of the lens? Okay, so it's kind of a weird equation in that all of our variables are down in the denominator. So another way to say this is the reciprocal of the focal length is equal to the sum of the reciprocal of the image and object positions. Now, when we do this with some numbers in here, yeah, it's fractions, but we're going to rely on our calculator, right, to quickly turn those fractions into decimals and make it easy to apply this. So that's the first equation, the lens equation that relates the focal length, the image distance, and object distance. Let's see, one other note. Yeah, di is positive, right, when the image forms on the opposite side, negative, like in case 5 that we just saw, if it forms on the object side. The other equations we have to do with magnification. Okay, so m stands for the magnification factor, right? So if the size were the same, m would be equal to 1. If the image were larger, m is going to be greater than 1. If the image is smaller, then m would be less than 1. Okay, so this is like the multiplication factor that's going to give us either a larger, smaller, or in some cases, same size image that we have. The h simply stands for the height of the image, okay? So another way, if we were to rearrange the equation to solve for the magnification factor, is to take just the ratio of the image height divided by the object height. But it also turns out that we can get the magnification factor from the ratio of the image distance divided by the object distance. And we put a negative sign in there to account for the plus or minus positive or negative values of the image distance. So this allows us to, if we know 2, we can solve for the 3rd variable here. If we are trying to find the magnification factor, we would need to know either the distance for the image and object or the height for the image and the object. All right, let's look at some examples of how we would apply this. So here we have a problem where we're given an object and we're given some parameters here. It says the focal length is 8 centimeters, right? So let's put that over here. The distance object is 32 centimeters, so that's the distance of the arrow from the lens. and the image height is 3 centimeters. Okay, now what do we want to find? We want to find the image location, how far from the lens, what the magnification factor is, and what the image height will be. Okay, so we're going to use our formulas. Now, we could use the graphic method just to kind of see what our answer might look like, right? So let's put in our 2 lines here, and we see that the image is going to form over here. So we should get a smaller image, means HI will be less than HO. It should also be negative because it's inverted. And the image distance, right, is certainly going to be less than the object, so less than 32, but greater than the focal length, 8. Okay, so you can use the graphical method to kind of test and see if your math answers are correct. Well, let's move ahead with the math. So we're going to use the lens formula. What can we plug in? Well, we're trying to solve for DI, so I'm going to rearrange this equation, right? If I'm solving for DI, let's put 1 over DI on by itself and subtract 1 over DO. Okay, so now we can plug our numbers in. So we get 1 over 8. 8's the focal length, 32 is DO. And we just let our calculator do the work here. So take 1 divided by 8 and then subtract 1 divided by 32. Just be careful of your order of operations. And then we can solve for DI. Okay, so if we take the reciprocal, right, 1 divided by 0.09375, we get 10.7 centimeters. So don't forget to take the reciprocal once you solve it in this way. So 10.7 centimeters, that means the distance from the image to the lens is 10.75. Now let's find the magnification. Well, we can use the ratio of DI over DO, because that's what we just solved for, right? So we're going to put in our 10.75. Notice we'll put the negative in and then divide that by 32, and we get negative 0.33. Now, what does that tell us? First, the negative tells us the image is going to be upside down or inverted, and the 0.33 says it should be approximately 1/3 the size of the object, which it kind of looks that way from our diagram up above. The last step is what would be the image size. Well, we're going to multiply the object height, right, 3 centimeters by basically 1/3 or 0.33, and we get a negative 1 centimeter. And again, the negative tells us that it's inverted or upside down. Okay, so there's an example of finding the image location and height using our lens formula and the formula for the magnification.
Almost 2,000 years ago, the Roman philosopher Seneca peered at his book through a glass of water. Suddenly, the text below was transformed. The words magically became clear. But it wasn't until a millennium later that that same principle would be used to create the earliest glasses. Today, glasses can help millions of people with poor vision due to uncorrected refractive errors. The key to understanding what that means lies with the term refraction, the ability of a transparent medium like glass, water, or the eye to change the direction of light passing through it. The eye has 2 main refractive surfaces, the cornea and the lens. Ideally, these surfaces work together to refract light in a way that accurately focuses light onto the retina, the layer of light-sensitive tissue at the back of the eye that works with the brain to give rise to vision. But many people develop refractive errors, either during childhood as their eyes are growing, or in later life as their eyes age. Imperfections in the cornea and lens cause refracted light to be focused in front of or behind the retina, making images appear blurry. People with refractive errors can still see color, movement, and light, but the details of what they're looking at are out of focus. People experience refractive errors in different ways, owing to differences in their eyes. In some, light refracts too much, and in others, too little. Eyes with a focal point in front of the retina are called myopic, or short-sighted. They can see close objects clearly, but those far away are out of focus. But when the focus point is behind the retina, people are hyperopic, or long-sighted. For them, objects close up are unfocused, but distant objects are crystal clear. Finally, some people have a cornea with a non-spherical shape that causes astigmatism, a form of out-of-focus vision that makes all objects seem blurred, whether close or far. As we age, our eyes face new challenges. When we're young, the lens of the eye is flexible and can change shape to bring images into focus, something called accommodation. This keeps objects in focus when we shift our gaze from far to near. But as we get older, the lens becomes less flexible and can't change shape when we want to look at near objects. This is called presbyopia, and it affects adults starting around the age of 40 years. Myopia, hyperopia, astigmatism, and presbyopia. Each of these is a refractive error. Nowadays, we can fix them all with glasses or contact lenses, which work by refocusing light so it strikes the retina precisely. It's even possible to correct vision with surgery, using lasers that change the shape of the cornea and alter its refractive properties. But glasses remain the most popular. By using carefully crafted lenses to steer light to exactly the right spot on the retina, a person's clear vision can be restored. We've come a long way since Seneca's discovery and the crude glasses of yesteryear. In 1727, a British optician named Edward Scarlett developed the modern style of glasses, which are kept in place with arms which hook over each ear. Today's glasses take their inspiration from that design, but they're also much more precise and personal. Each pair is tailored for an individual to bring out their unique powers of sight. So if you're one of the 500 million people with a problem with close or far vision, or both, there's a pair of glasses out there waiting to reveal a whole new world that's hiding in plain view.